Number two, plastic deformation, which is the past point B from point O to point P. E to P, the stress strain curve is no longer straight, but remain elastic until the point B. Here, it's not a straight line. It's very obvious here. It's not a straight line. However, it can handle a bit more force and it will still act in an elastic way. It will still handle the force applied to it. So, when the stress is removed, the rod returns to original length at O. This point is called the yield point, which means if we applied force and the stress strain curve goes over the point B, the rod does not return to its original length. For example, from point A, it returns to O prime. From point A, because we moved past the point B, the force applied moved it past the point B. So it will be from point A to point O prime. Now, the rod has, in a sense, begun to fail as it remains permanently deformed because the force applied or the stress applied on the rod moved past the elasticity point. It will stop acting like an ideal spring. So, when the stress strain applied to it breaks past the P point or the yield point, after removing the stress applied, the rod begins to fail, begins to break, and it never remains to its original form and it will be permanently deformed. This plastic deformation, the material flows under stress and doesn't return to its original shape. It behaves like a plasticine, okay? Because it doesn't handle the force or the stress strain applied to it. Each material, okay, have a yield point, or you can call it a no turning back point. Once the stress strain applied to that material, to that object, the object will not return to its original form once the stress is removed. It will be permanently damaged or permanently deformed. We call this a plastic deformation. Number three, mechanical failure. At the point D, the stress is greater than the material withstand. We reach here to the point of deformation. However, if we still applied a stress strain, it will be from point O to point D. And the point D is where the stress is greater than the material withstand. This is the breaking stress. The difference between the mechanical failure and the plastic deformation. In the case of a plastic deformation, the rod or the object will still keep its shape, okay? However, it will be deformed. But the point of mechanical failure, or in the diagram, you can see here, the point D, it will break and will not be just deformed. It will break, or this is called the breaking stress or the ultimate tensile strength. We have here the degrees or the stress strain forces that withstood by each material. You have mild steel, which is 0.841 Pascal. You have cast iron, 0.200. The concrete is 0.005, which is 5 in 1,000. Carbon fiber can withstand 7,000. Bone, 0.130. And wood, 0.90 to 0.18. Now, we're going to talk about something called elastic modulus or Young's modulus. Tensile stress is proportional to tensile strain. as you can see here. Tensile stress equals elasticity by tensile strain. The strain is proportional to stress according to Hooke's law that was in the beginning of this lecture. The constant of proportionality is E. So, tensile stress equals the constant of proportionality, tensile strain. To know the value of the constant, we divide tensile stress over tensile strain. The constant of proportionality is a measure of material stiffness. To know whether a metal rod, wood, bones, whatever the material is whether it's stiff compared to the other. It's very important to know that the constant of proportionality when we divide tensile stress over tensile strain. Composites. We have types of composites that we're gonna take one by one and learn. Steel reinforced concrete. Steel cables give tensile strength. The concrete resistance to compression. Bones. Collagen fibers, which have high tensile strength embedded in a stony matrix of calcium hydroxyapatite crystals. Okay? Combine tensile and compressive strength. So, this means steel reinforced concrete. It means that the steel rods that are embedded in the concrete. Okay? The steel part of the cable, this is what will give the part of tensile strength. The concrete will give the resistance to compression. يعني جزء الستيل أو جزء الكيبلات الستيل هي راح تعطينا هاي التنزل سترينث، وجزء الكونكريت هو راح يعطي المقاومة للضغط اللي المسلط على الستيل كيبلز اللي مثلا راح يستخدموها بالبناء أو بالعمارات إلى آخره. Okay, that's why they reinforce steel with concrete. يعني لهذا يقاومون الكونكريت بالستيل، لأنه الستيل وحده ما راح يعطينا ريزيستنت معينة للكومبريشن أو الضغط المسلط عليه. بالنسبة للبونز، البونز بتتكون من كولاجين فايبر اللي هي عندها هاي تنزل سترينث. اوكي، نفس حالة الستيل رينفورس كونكريت انه هي ما حتكون وحدها، راح تكون مدعمة بشغلة راح تخليها تقاوم الضغط. بحالة البون هاي الشغلة اللي راح تكون محيطة بالفايبرز حق يسموها ماتريكس. اوكي، هذا الماتريكس راح يكون محيط بيها ويساعدها على تقاوم الضغط مالتها، عفوا الضغط المسلط عليها. هذا الماتريكس متكون من calcium hydroxyapatite crystal. This combination is known for being resistant or rigid. This will give the strength for the fibers to resist compression. In this photo, this is an intricate explanation of how the compact, of how the bone, or what the bone is made of. We can look at part or the picture A. This outside layer is the compact bone. The inside of the compact bone, there is a spongy area or a spongy material called a spongy bone. The spongy bone is usually softer than the compact bone, so it will need some type of support which the compact bone will provide. These circular canal-like objects or drawings are called central, or what they are called Harvesian canals. This one. Osteon is a Harvesian system. So the Harvesian canal is a part of the Harvesian system. These lines are the circumferential lamella. Okay? Circumferential, circumferential lamella. These are called lamellae. The difference between circumferential lamella and the lamella is their position or their location. This one is called circumferential because it's on the exterior part of the bone or the lateral part. And this one is the internal part. They have the same function and they have the same composition. They are just different in location. You can see here we have perforating or Volkmann's canal, and these two are endosteum lining bony canals and covering the trabeculae. This whole structure of bone is covered by an outside or external sheath, which is called perforating Charpey's fibers and periosteal blood vessels, and this one is periosteum. So if you want to look at the structure from outside to inside, we have periosteum and then periosteum blood vessels, and then the perforating fibers. The perforating fibers are finer than the blood vessels, and so on. Let's take a cross section. It's not a, or not a cross section, a part of the Harvesian or of the Austrian system. We can see it's made of the yellow nerve, of a vein, and an artery. You can see here the canaliculi and the osteocytes in a lacuna. The caniculi, which are these two miniature uh, structures, okay, they are miniature channels that veins the zone go through. You can see here a cross section. These parts, the beige ones, are the interstitial lamellae. Okay. Of course, interstitial lamella. The lamella is a thin structure in the bone, of course. Insert interstitial, and this one is a lacuna with an osteocyte. Let's look at what the osteocytes are made from. The whole structure, this whole structure, is called an osteon. This hole or the circle in the middle is the Harveysian canal. Each part of these purple dots that's in front of you is an osteocyte. And the fine lines that you can see are a caniculi. Let's take a further picture of it. The orange structure is an osteocyte, and the small dot in it is the nucleus, because of course an osteocyte is a cell. Each cell needs to have a nucleus and a nuclei. So the nucleus in this structure is here in the osteocyte. The beige part, the background the beige part in the background is the matrix of carbonated hydroxyapatite crystal that we mentioned before gives the collagen fiber a tensile strength. And this is the chemical form of it. Calcium 10, PO4 by 6, OH by 2. Then we're going to look at each individual osteo. Of course, we have to have a vein, an artery, and a nerve. So you can see here an artery with capillaries, a vein, and this one is the yellow. The yellow one is the nerve fiber. All of these together are structured in the central canal, which is this uh, brown part, like a hole. It's covered in a structure called a lamella, and the lamella is surrounded by the collagen fibers. The collagen fibers have a twisting force. As you can see from these lines in green, it means they have a twisting force, clockwise and counterclockwise. Nutrients diffuse from vessels in central canal. Alternating direction of collagen fibers increases the resisting to twisting forces. Of course, as we know, as we said before, it has a twisting force. By changing or alternating the direction of the collagen fibers twist through, this will increase the resistance, which when increasing the resistance, the force will also increase. But this will be protected by this one, which is matrix of carbonated hydroxyapatite crystals. Of course, nutrients go through the vessels in the central canal, which are these. Wolff's law. According to Wolff's law, the bone is a dynamic tissue and adapts to load placed upon it. As you can see here, is a diagram of a bone of the human body. The bulbous part at the right, this one, we call this a head of a femur. The load of the body weight will be applied to the femur. The femur part of each bone is the upper part directing the movement of the body, okay? Like in the knee, or the hip, or the shoulder, okay? This bulbous part. The load of the force of the body weight is applied to the femur. As we mentioned before, in the rod, when a force is applied on the rod, because the structure or the general form of the bone is somewhat similar to a rod, the force will be applied in a direction from above to below. So the compression will be from above to below. From beginning of applying the force inside the femur, moving along with the bone, reaching, let's call it the midline. Okay? As we mentioned in these before, here, elastic deformation. This will withstand the force applied. You can see here, maybe in the middle, the point of no stress. When the load of or the body weight or the force is applied, let's say from outside inside, the compression, the movement of the compression will be from the outside to the inside. The tension will move from inside to the outside in a point of resistance. As you can see here, this is the femur and the load is applied here. The purple lines are the compression lines, as you can see how it goes from above to below. While the tension lines goes from inside to outside, inside to outside. The spongy bone sits at the end of the femur and works as a shock absorber. You can see here the tennis player. She's holding the racket in one of her hands and the other one is not. So the hand holding the racket will be called the serving arm, and then the other one will be called the non-serving arm. We can see the difference in both in the trained hand, which is the serving arm, and the non-trained hand, which is the non-serving arm. This is a cross-sectional dimension of the humerus. The deep brown lines you can see in the inner circle are similar in thickness and in shape. However, in the serving arm, which is the trained arm that will be applied, that will have more stress and more load applied to, because the tennis racket is quite heavy. So the tennis player on the trained arm, the served arm, will need more support. How does the human body adapt to support the serving hand or the serving arm? Is by adding bone matrix. The deep brown lines are added bone matrix, concentrates added stress. Of course, every human is either right-handed or left-handed. If you if you have the functional arm, let's say you're a hand-righted person, you pick up things with your hand, you write with your hands, you drive with your right hand, of course. So let's call the right hand of yours is a trained hand, or let's in this case a serving arm. While your left one, you also use it. You of course, as humans, we're not just going to use one hand. You also use your left hand, just not in the same frequency and concentration as your right hand. So when you apply more pressure, when you apply more force to your right hand, your body will adapt to prevent your bones on your right hand from breaking or having a fraction by adding extra matrix. Your left hand will of course have a matrix. Every bone in the body is embedded in this matrix, but in different thickness and according to the function of the bone in the body. So, to this tennis player, her serving arm is used more. Let's assume it's her right hand. So, of course, naturally, she will have, or the bone will have, added bone matrix to counteract the stress. Cracks and fractures. Once a crack appears in a material, it can spread easily as the stress is focused at the tip of a wedge-shaped crack. So you can see it on the left.